Hey everyone, today let's look at the problem 494 target sum. You are given an integer array nums and an integer target. Okay, you want to build an expression out of nums by adding one of the symbols plus and minus before each integer in nums and then concatenate all the integers. So basically, if you see here, for each of this, I could either add or do a subtraction. Okay. Return the number of different expressions that you can build which evaluates to target. So at any given point, so let's take an example to understand this very clearly. So at any point, I could either have +1 or -1, and each of them can take different paths. So that means this can again be another +1, -1. So like that it can go. And the thing is, like by doing so, in which all are the paths which will finally give us this target 3. Now, as you can see here, this is an explanation. If you do a -1, then a +1, +1, +1, +1, that gives you 3. Similarly, these are the other paths. Now, let's try to understand this problem a little bit visually. Okay, so now let's think about a brute force approach, which is nothing but a depth first search here. And see how we can arrive at the different values. So you can see here, to start with, our sum will be 0 because we haven't added any element. Now I took an example where all the inputs are 1, okay, and we have 5 ones. Now at this point I can either add the 1 or I could subtract the 1. I'm not drawing this fully because it will be a big tree. So now let's explore this path. Okay, so now our sum will be 1. This could again be a +1 or a -1, and so this would end up in 0. Here also you have a path, but let's explore this path alone. So you can see here, now this is the third one actually. Okay, now at this point again you could have another +1, which could end up, you can add it, that could give you 3, or you could subtract it and get another the 1. Same way this goes on until we do all the ones, as you can see here. And you can see, right, in this example, at least in this path, you see 3 3s. So at the end of the day, if you had explored all the paths, you would have seen 5 3s. I think that's the answer. So you would have seen the 5 3s actually. Okay. But if you see this approach, this is an expensive approach, right? So it will, at each point you have 2 options and the height of your tree is n. So that means your time complexity will be 2 raised to n. Okay, so it's like 2 into 2 into 2 into 2 up to n levels. So that means you will have 2 raised to n as your time complexity, and since the depth is n, your space complexity will be order of n. But if you see here, by doing some optimizations, you might be like our normal caching mechanism, you might be able to improve its time complexity. The reasoning is that if you see repeated work here. So for 2, you know that this will give you 1 path. Okay, so you could actually reuse it at this level. So like that, you could actually reuse it at different points in the in your DFS tree. Using this caching mechanism, if you cache for a given index and sum, so that is at that sum for that given index, okay, then you will actually improve your time complexity. So that means your time complexity will be because you have to find n into total sums. It need not be total sums. That would be the worst case. You can take it as t, which is somewhere less than total sums in an ideal case. So your time complexity will be order of n into total sum, and your space complexity, because you have to store that many cached values, so will be also n into total sums. Okay, now let's just code this up. Okay, now let's first of all just do a DFS to make our life easy. Okay, so this will be 0 index, sum will be 0, you will have nums and target. Okay, and your return will be all the possible paths where number of paths where you could hit your target sum. So now this will be underscore DFS. So I'm just using DFS here. It is indi, your current index. This is your current sum. Okay. Then we could have something like, maybe I'll rename this to suit this as current sum. Okay, and you will have in the other nums. You could do this better. Maybe if you had use a lambda function, maybe this will be much you might have lesser arguments, but I'll keep it simple here. Okay, so this is what we have. So I think I have everything. Yeah, so now let's first get the exit condition. So this is where we have reached the end of the array. So if we have reached the end of the array, then we can return 1 if current sum is equal to target sum. So that means at that point we'll send 1, if not we'll send 0. Okay, so that should take care of our exit condition. Now what are our options? So if you see here, our total will be actually current. So we have two ways, right? Either to increment, to add it, or subtract a given index. So it will be I plus 1 comma cursum plus nums of I comma nums comma target plus. Okay, so this will cover one particular case. Now the other option is basically where we subtract it, and we will take the total count. Let's see. So as you can see here, as explained earlier, the time complexity. So let's put this as DFS brute force. Time complexity will be order of 2 raised to n. Space complexity will be order of n. Okay, so if I just run it, I'm not going to submit it. So let's see what is the issue. What happened? Let's see. It is target. Oh my bad. So it should be target. Okay, so let's just run it. Okay, now let's do the caching as explained earlier. So what we can do is, I could just create an unordered set, map, okay, which will take in int and will be dp nums.size comma target. This will be basically sorry, my bad. Okay, this is what we'll have because it's an unordered map. So the first integer, basically it will be a map of index comma current sum. Okay, now it's a small thing here. So this will be pair and this will be pair output. So for the given pair, I will have the, for the given current sum, I will have the actual value. Okay, this is what we are going to have. So we'll have to also put a hash function, because it's the pair is we are passing pair as our key. So I'll just put the hash function also. It will be size underscore t operator const pair defined and b. Okay, so let's put auto h1, basically the hash function. It will be p dot first, just p. It's not very critical. So this will be p dot second. Okay, so that should cover the hash function. So we'll pass dp here, and we will also take in dp as an argument. Node dot map pair find dp. Sorry, I have to also pass the hash function. Okay, I know we are having so many arguments, but yeah, let's just continue. Alright, so here we will basically check for the if dp dot find I comma cursor okay, not equal to dp dot end, return dp of I comma cursor. Okay, and here what we'll do is we will also cache it, dp of I comma cursor is equal to total. So let's see. Okay, dot find. Okay, I think I have one bracket extra here. So okay, oh sorry, I have to pass the dp also. Same here. Okay. Okay, let's submit this. So this is quite a good solution, but I think we can improve this further. All right, so now let me explain you some approaches here. Okay, so to tell you frankly, this is how I solved this problem. To further improve it, actually I also needed some help, so let me give you what I learned. Okay, now let's just do the DFS with caching using a DP array. So previously, as you saw, I just used the DP map data structure to do all the implementation. So yeah, let me get the mouse pointer also. All right, so for this becomes very important. Now, if you see here, the total sum that we can actually form using this array is 5. You can see here, right? So it's 1 plus 1 plus 1 plus 1, and it can range from a value of -5 to 5. Okay, the reasoning is that if I just do a -1, -1, -1, -1, -1, that also will be -5. So your cached value will be between -5 and 5. Okay, but the problem is, so that means if I have an array starting from -5 to +5, that should cover for all the values that I would cache. But the problem is we cannot have a negative index for array. Now what can we do? So what we can do is we can create an array of 2 into total sum, that is total sum plus 1, and then represent -5 to 5 the values in this range in 0 to 10. So what would happen is, assume that you have a sum something like 2. Okay, at this point you have 2. Okay, then that can be represented by in the array as total sum plus 2. So then that means it will be in 7, index 7. Similarly, if you have a sum of -2, then it is like 5 minus 2. So it will be represented in the index 3. Now this will not give us a lot of improvement. Hey, I think I have to correct this. This is n into total sums. Okay, the space complexity. All right. So, but let's now just code this up. Now, I'm just going to continue on this. Okay, just to make a, yeah. So, in the above code, this is what we had, right? So now instead of this, now I think I'll just take out all these DP portions. Okay, just to make it simple. I can better code it up itself. So it is like now we'll have a vector int. So first I will need to do an accumulate. So that means I will have to find the total sum. It's equal to accumulate. So basically it's just a one-liner for finding the sum of all the elements in the array. So this will be, so this will give you the total sum. So now we will have to create a DP. Okay, all right, such that, as I mentioned earlier, it will be nums.size and let me just add some nodes here. DFS with caching using a DP map. That was n into total sum. Okay, and okay, all right, and then space complexity was order of n into total sum. All right, now here what we will do is this will become so vector int 2 into total sum plus 1 comma, I'll just keep it a different value. Okay, so that looks good. And now this is our DP. So here what we'll do is we'll just pass. So I'm just keeping the original code and modifying it slightly. Okay, and I can explain that portion. Okay, and this will become and DP. I don't need the hash function anymore. I'll just take that out. Okay, so let me make this much simpler. Now if DP of I cursum, so now what happens is I cannot use cursum. So what I'll do is I'll just add this to, so I have to pass one more argument here. I have to also pass total sum. Okay, rather than having to do an accumulate every time, I'll just pass it around. So we'll just pass it around. Okay, and what we'll do is we will check total sum plus cursor. Okay, this is how we stored it. We not equal to int min. Then what we can do is return that. Return dp of I total sum plus cursor. Okay, here we will have to also pass total sum. All right, the remaining code we will keep it same. Okay, then here we will just make it as dp of I total sum plus cursor equal to total. Let me just check the code once more. So this is where we will check the caching. Okay, and the other part should remain the same. Only thing is, when we store, we will store with total sum plus current sum. Okay, so let's see. Okay, so as you can see, it is quite good. Now let's see the next. So this also, if you see, instead of this one, what we did was we just did with the dp vector. So okay, now the next thing is, let's try a bottom up approach. All right, I know this is a busy slide, but let me explain this. Now if I take for the original array, if I now represents this in a 2D matrix, okay, so if you see here, the row is represented by total sum plus current sum. Okay, so as stated earlier, now our at any given point it is represented by total sum plus current sum, and this is our input array. Okay, now if you see here, for the first value, since it's all 1, at any point I can just add 1 or subtract 1. Now total sum is 5, so in this case, if I let me start with subtracting 1. So if I subtract 1, then that means, so let's take this row alone, then that means all this is going to be like if I subtract 1, it's 5 minus 1, so that means it will be 4. So I'll come to this index and I'll be just subtracting this one, and for adding 1 I'll just set value 6 to 1. Okay, I hope this is clear. So total sum is 5, and to subtract 1, this will be 1, this will be 4. So that means I will have one instance of 4, and I will have one instance of 6, because I can add 1. All right, now let's jump to the next case. Okay, now what happens is, we will continue iterating until we hit a point where the previous one has a 1. Okay, and then we will subtract 1 to this, so this will become 1. Okay, I'm jumping a gun here, so this also will become 1. All right, now we will come to this index 6 here, so that will result in this value adding so that adds this one also to 5. So that means to reach 5, there are two different ways. When we tell 5, it is actually referring to value 0. So either I can come through this path or I could come through this path. So I could have two different ways to reach this location. Same way, 7 can be created by, or whatever we call as +2 can be created by this one from here. If we add 1, we will get it here. Now I'm just populating the remaining table. Okay, feel free to try populating this table. That's the easiest way to figure this out. Okay, I'll always encourage to try this out. Okay, now another critical thing here is your total sum plus target, which is 5 plus 3, represents the sum, target sum 3. Now that means this particular row and this particular column and the last row will represent the actual value that is represented by that is basically the output for our data point. I hope this is clear. Now if you see here, we could further improve this. Here also the time complexity is order of n into total sum and space complexity is order of n into total sum. But you could, as you can see, at any given point we just need the current row and the previous row. So we could do a space optimization and get this to order of total sum. So let me do both here and show you how this works. Now let's start with a clean slate here. So let's get this with a 2D array. There's a corner case that we will have to handle here. I'll just put it here up front. So it's a case where if target is greater than total sum. So it could be should be ABS because it could be negative also. So in that case, return 0. So if our target sum is bigger than this absolute value, bigger than this total sum, then otherwise we will have an array out of bound access here. So to avoid that, we are doing this way. Now here, as mentioned earlier, what will happen is, let's just populate the first row alone. So that is dp of, so here this will be represented by 0. Okay, so this will be dp of 0, and what we will do is we already have the total sum. So total sum plus nums of I, nums of 0 will be equal to 1. So, and hey, there's one interesting thing here. I made a mistake when I coded it first time. You have to give this way. This is a case where your nums of 0 is 0. So then that means what will happen is you have two different ways to reach 0. So that we have to take care here. Okay. Now let's do one thing. R is equal to 0. R less than nums dot size plus R, and for auto C is equal to, so first row is already taken care, so we can just go to the second row. I'll make it more readable. I'll just make it as index and index. Okay, feel free to do it differently. I am just to make it more readable. Let me also make this int. I will just start with minus total sum. Okay, car sum less than or equal to total sum, because these are the values that it can take. sum. Okay, you could even go this way where you start with 0 and go up till 2 into total sum. That's also another way, but yeah, I'm just going this route, okay, to explain it much clearly. Now what happens is your if dp of r minus or like index minus 1, okay, as explained earlier, so we have to reach the first point where it's a non-zero. So that means we will have to add cur sum plus total sum. Okay, this greater than 0, then in that particular case alone, dp of, as I explained earlier, index of cur sum so it will be cur sum plus total sum plus nums of I. Nums of index will be equal to plus equal to dp of basically this value. Just being lazy to type. Okay, and similarly, as we know earlier, this will be equal to the minus part also. So either I have an add or I can subtract. So I have to take care of both. So that should cover these two cases. And if I return dp dot back of target total sum plus target, I should be good. Let's just see how it goes. Okay, so it's cur sum total sum. Okay, let me see what was the thing. Greater than, oh my bad, again bracket. So this is this way. Let's try running. Okay, this looks good. Let's try submitting this. That looks good. Okay, now I know this is a long video, but let's see. Let's take all the cases, right? So bottom-up approach with the 2D array is same time complexity and space complexity as the one I explained above. But now let's see how to optimize the space complexity. Now, if you see here, you can see from the code itself, right? You only need in these places only need have a dependency on the previous row. So what we can do is we can optimize this code such that we make it this way. Okay, I'll explain to you a little bit further. So now this will be our let's put this as our next DP. Okay, so this will be our next DP, or I can make it even much simpler. Let this be DP itself. Okay, and this, let it be okay, I'll keep it simple. So let's put it as DP. Okay, not that good with namings, so I'll keep it simple. Now what happens is this will be representing the previous row and this will represent the next row. Okay, So just to be clear, this is here the current row, and this is our next row. Okay, so here, as you can see, now this will become next. Okay, next, and this will be dp. Okay, and at the end of this for loop, we will have to basically assign dp to be next, so that it will be an input for the next round of iteration, and at the end we can just return this value, because here also we again assign it, so we'll put it that way. Let's try running this. Something went wrong. Let's see. I have it here. Okay, then we have this thing here. Oh, EP of total sum plus sum 0. So we took care of that. Then it comes here. Then we tell, no, my bad. So this should be dp, and this should be this one. So okay, so that looks good. Okay, that's it. This is a long video. So I explained so many options. So I think the first solution was easier, and most of us would have got it there. Yeah, if you want to further optimize the space, that's where the challenge is. So this will come to this is bottom-up approach with space optimization. Okay, that's it for today. Thank you. Have a good one.